Okay, in this video we will start looking at the motion of rocks in space, and these rocks will be considered as free, that is, there will be no force acting on them. Okay, and as we have seen that these rigid bodies or rocks are generally referred as top, and they come in different varieties. They could be spherical, completely spherically symmetric. Okay, so you say that spherically symmetric rock as a spherical top. If your rock is symmetric about some axis, you say you have a symmetric top, and if it does not have any symmetry, then you say asymmetric top. Okay, so let's imagine some rock is moving around in space and it's spherically symmetric, and then we want to know how it will be moving about. And as before, in the last video, we would not be looking at the motion of its center of mass, so we are only looking at the non-trivial part, the part due to rotation of this rock. Okay, so first case of spherical rock is very easy to look at. So let me write down here spherical rock. Okay, so in this case, as you know already, all the principal moments of inertia are equal. Let's say the common value is I. Okay, and then if you want to know the intrinsic angular momentum m, let's look at the kth momentum. K could be 1, 2, or 3. Then this would be I omega k. Okay, so that's what it is, which means that intrinsic angular momentum is parallel to the angular velocity. Because there are no forces on the top, your angular momentum is not going to change. Okay, and which also implies that the intrinsic angular momentum is not going to change, because the part which describes the motion of the center of mass, that will also be conserved. So that would mean that the intrinsic angular momentum, which we denote by m, is also going to be constant of time in time, which means that the angular velocity omega, okay, is also going to be constant. So the the axis about which the body which is spherically symmetric is going to rotate is not going to change with time. Okay, in general, you know that omega vector is going to change with time, meaning the axis of rotation is going to change with time. But for a spherical top, because of its highly symmetric construction, it's not going to change. Okay, so which means the picture is this: the body keeps spinning or rotating about a fixed axis at a fixed rate. Okay, so that's the simple motion that it is going to execute. Okay, let's now reduce the degree of symmetry that you have, and let's say we don't have a spherically symmetric top, but you have a symmetrical top, meaning your rock which you are looking at has only one axis of symmetry. So now I want to look at symmetrical top. And again, it's you can again imagine a rock which is moving freely deep in space. It has been thrown in some manner. Okay, and just now you just want to know how it moves around. Okay, so let's see what we can say. If you look at the intrinsic angular momentum, then m1. So I'm imagining that I'm decomposing the angular momentum of this body. Whenever I say angular momentum, I mean intrinsic angular momentum. So this m, because there are no forces, this is going to be conserved. So let's say you think of a moment, one particular instant, and at that instant you are going to decompose this m into into its components about body axis. Okay, so let's say at a given moment the principal axes of the body are oriented in some manner. Okay, and at that time you want to decompose m along those directions. Okay, so that's what we are doing. So m1 will be I1 omega 1, m2 will be I2 omega 2. That is what we have seen already. That's the general thing. And the third component will be I3 omega 3. Now what I'm going to do is look at where x3 points. So the x3 is the by x3 I'm denoting the third coordinate which is attached with the body. Okay, and I look at the vector m. So vector m is going to be fixed in space, and at that instant I'm looking at x3 direction. So this direction of m and the direction of x3, they define a plane. Okay, any two lines define a plane, or any two directions you can take, and that will define a plane. So that is the thing which I'm going to utilize now. So let's see here. I have drawn already this setup. Don't look at x1. Okay, this I will explain. I wish I had not drawn this already, but just to save a little bit of time, I've done that. So here is the direction m, which is not going to change with time. At the moment I'm looking at things, let's say x3 axis is in this direction. Okay, and I say that the plane which is defined by m and x3 is the plane of your screen. Okay, so that is the plane we have. So your m and x3 are in your screen. Now how about x1 and x2? Well, they have to be perpendicular to x3, but because your body has symmetry about x3, you can take x1 and x2 to be in any direction, right? That's what we discussed earlier also. So what I'm going to do is I will choose to put x1 direction in the plane of your screen. Okay, and x2 will be of course perpendicular to the screen. So this choice I can make because of the symmetry of this object. So here we are. So all the three, x1, x3 and m, they are all in the same plane at this instant. At the next instant, of course, things will change, but at the instant which we are looking at, everything is in the same plane. So if I do so, then m2 is 0 because m is in this plane, m is in x1, x3 plane, so it does not have a component m2. Okay, so there is no m2 component, which means m2 is 0 at this instant, which means omega 2 is 0. Okay, that's good, which means omega has only omega 1 and omega 3 as the components, and omega 2 is 0, which means your vector omega lies in x1, x3 plane. It is omega 1, 0, omega 3, right? So this is a vector which is lying in x1 and x3 plane. So I want to draw that, and of course, as you know, it will not point along m. So let me draw that. Okay, let's see if I can do it. How should I? There is a yes. Okay, looks like it's going to work. Perfect. I think this is good. Let me use some color. Maybe no color. Okay, fine, no color. Okay, let's use red. So so this is the vector omega, okay, and omega is also going to be in this plane. Okay, that's nice. Let me cross it. This is my vector. Omega. Okay, and that is fine. Now I want to first tell that the angle which axis of the top, this x3 is the direction of the axis of the top, okay, the symmetry axis. This makes an angle theta at this instant. Let's say this is the angle theta. Okay, that's good. Now yeah, now let me draw a line parallel to M. Let me draw a line parallel to M. So this should be vertical. Let me, maybe I should make a nice no. Okay. Yeah, it works. Okay, so this direction which I am about to draw is parallel to the intrinsic angular momentum. Let me yeah, put just, this looks perpendicular. Yes, it looks. Okay, so if I or maybe I should just fill it up. Okay, and yeah, good. So this one I'm going to call this vector from here to there as omega PR. Okay, PR for precision. You'll see why I have used this subscript. So anyhow, it is just the projection of omega along the direction of M. Okay, and then this remaining part, so this vector from here to there, let me again bring this. Okay, it's here, and then I take it and bring it here. Perfect. This vector this vector is what I'm going to call as omega. What happened? Yes. Omega A. Okay, I call it omega A because this is along the axis of symmetry. Okay, A means subscript A means axis of symmetry. So I have written my angular velocity vector as sum of these two vectors, where omega A points in the direction of the axis of symmetry and the other one points or is along the direction of M. Okay, so that's how I decompose it. That is good. Now let me see. Yeah, so let's drop a perpendicular here. So I project omega along this direction, which will be omega 3. Okay, from here to there is omega 3. Okay, third component of the angular moment, angular velocity. Okay, and then this anyway is omega A, and this piece from here to there is omega precession times cos theta, because this angle is also theta. So this will be omega precession, okay, omega PR cos theta. Okay, that's good. Now let's have a understanding of this. Perfect. Okay, so first thing is, let me write down a few equations now. I think I've written down everything. Yes, correct. Okay, so first is that my omega is omega precision PR plus omega A. Okay, that's the decomposition of this vector we have done. So let me, I think I've said already. So here omega has been written as a sum of omega PR, which is parallel to M, and omega A, which is along the symmetry axis of the top. Okay, now from the figure it is very clear that you can write omega A plus omega PR cos theta. This is omega 3, right? So here you have omega 3 from here to there, and this is sum of omega A and omega PR cos theta. That's what I've written. So let me call this as equation 1. Very good. Okay, and from this I can conclude that omega A is omega 3 minus omega P cos of theta. Just taken one term on the other side. And also your omega PR sin theta is omega 1. You see, if you take this omega and project it along x1, that's what you get, right? It's equivalent to projecting it's equivalent to projecting your omega PR along x1 axis. Okay, so your omega PR sin theta is equal to omega 1. That's correct. Correct, that's correct. Okay, now I know my M, okay, angular momentum, and I would like to determine these omegas, and what I'm interested is in omega A and omega PR. So I'm going to use my omega 1 as m1 over I1 and omega 3 as m3 over I3. Okay, that's what I'm going to use. So substituting that, I get, let me write, substituting m1 let's say mk I k omega k, there is no summation over k. I get the following. I get, you can easily check, that's trivial, that omega precession is m over I1. Okay, that's one result I have. So this says that your top is rotating at a uniform rate about the direction of the angular momentum. See, the m is not going to change with time, it's going to always point in the same direction. And you are looking at a vector omega PR which points along m, which means that when you are looking at omega PR, it corresponds to the motion of the rigid body as a rotation about this axis, omega PR as the axis, right? So that is why it corresponds to a rotation about the direction of angular momentum, and that is what we call as precession. Okay, so let me write it down. This corresponds to the axis of the top at a uniform rate about the direction of angular momentum, about the direction of okay, that is fine. And then the remaining thing, let me talk about. So my omega A is, where is it? I think I wrote it before, is omega 3 minus omega p cos theta. So this is the equation I'm using. Let me write it again. Omega p cos of theta. Okay, and what is omega 3? Omega 3 is your m3 over I3, but your m3 is m cos theta, okay, minus omega p we have already found, m over I1, and the cos theta factor is here anyway. So your omega A is m 1 over I3 minus 1 over I1 cos of theta. Okay, so that's the omega A, which is in the direction of x3, so it corresponds to the motion of your top about the x3 axis, which is basically the angular velocity of the top spinning about its axis. Okay, that's the spin of the top about its axis. That's what your omega A gives. And omega PR is giving you the precession of x3 about m. Okay, now I want to establish that the cos theta is a constant in this problem. So for that I would like to utilize the fact that the kinetic energy T is a constant because there are no forces on this body, and I write T as half two square plus half I3 omega 3 square. I believe I have done this already. Let me check. We were looking at, correct? Okay. So here you see we wrote down the kinetic energy as sum of these two terms, and you had omega j, I, j, l, omega l. All you have to do is now go to the principal axis. So once you're in the principal axis, your I will be diagonal and it will have components I1, I2, I3, and this will become I1 omega 1 square plus I2 omega 2 square plus I3 omega 3 square, and each of the terms will be multiplied with a half. That's what I'm using now. That's what I'm writing now. Okay, and the instant at which I'm looking everything, omega 2 is 0. You remember that. Your vector omega lies in the x1, x3 plane. Okay, so omega 2 is 0, which means your T is half I1 omega 1 square plus half I3 omega 3 square. And if I again substitute what omega 1 and omega 2 are in terms of angular momentum, you get half m square sine square theta over I1 plus cos square theta over I2, or sorry, I3. Okay, because T is constant, m is constant, you conclude that your theta is constant. Okay, which means that the body is going to make a fixed angle with respect to m. The x3 is going to make a fixed angle with respect to m. This theta is not going to change. The rock is going to spin about its axis with angular velocity omega A that we have determined already here. Okay, and it's also the axis also x3 axis is also going to precess about m, and it is again going, x3 is going to move at a uniform rate about m. It will keep going like this. Okay, and the angle will not change. That's the general motion of a free rigid body which is symmetric. Okay, but here you note that the direction of m and omega were not same. If they were same, if they were in the same direction, then what would happen? I'll leave for that you to figure out. Should be easy. Okay, that's good. And maybe one more thing. Yeah, I will also leave you to figure out what happens if your I3 is smaller than I1, or if your I3 is bigger than I1, because there will be a difference in sign in these two cases. Okay, so that is another thing I would urge you to think about. So that's the motion of a symmetric rigid body in free space, and we'll continue more on rigid bodies in the next video.